Hey y'all.
Good morning, Mr. Converse.
What's up, y'all?
Good morning.
Good to see ya.
Likewise.
We got one more coming, I hope.
Okay. Hope we get a full class today.
That's what I'm hoping.
Yeah.
All right. So, we need Saniqua. Where's Saniqua? All right. Hold on to that for now. Okay. All right. Today, we're going to start to look at the components of your diet and talk about what role they have in maintaining your health. And we're going to begin with carbohydrates and fats. Okay. So, organic compounds get that name because they all contain the elements carbon and hydrogen and often oxygen. Okay. Um, the reason that life is based on carbon, all the molecules of life that we're going to talk about are carbon based, like proteins and carbohydrates and fats and a lot of other molecules that make the body work are also carbon based, including hormones and um, immune proteins. Carbon can do one thing that none of the other elements in the periodic table can do, which is that carbon can form rings and chains with itself. Okay. And that means you can build a lot of neat stuff with carbon. Okay. You can make long chains. You can make chains with rings. You can make rings and rings, which means you can build molecules that have a lot of different shapes, and that's part of what allows them to do a lot of different jobs. Okay. We say that carbon is electroneutral. Okay. When atoms, which are the building blocks of matter, come together and connect with each other, they form something called chemical bonds. Okay. There's two kinds of chemical bonds. There are covalent bonds in which two atoms will share electrons between them, and the electrons are kind of what hook the atoms together. Okay. And then there are ionic bonds in which one atom loses electrons and one atom gains the electrons, and that means that they have opposite electrical charges, and that attracts them to each other, and that's what holds them together. Okay. So what we want to do here for just a second is talk a little bit about elements and atoms before we jump into organic compounds, so you can sort of get a grip on what we're talking about. So let's just real fast go over to a little discussion of chemistry, and this will help you sort of get a grip on this. Okay. So matter and energy and empty space are what make up the entire universe. Okay, that's the sum total of everything that's in our existence, right? Energy is the ability to do work. It comes in many forms. Matter is anything that has mass and occupies space. Okay, it comes in three forms: a solid, a liquid, or a gas. All right. A solid maintains its shape and has a definite volume. A liquid forms to the volume of its container, like the water in a glass. And a gas touches every part of its container, like the air in the room. Okay. And what makes those different states be that way is the amount of energy of movement that the atoms or the molecules have. Okay. The more movement you've got, the more changeable your shape is, right? So a solid, the atoms or the molecules that make up a solid, they don't move very much. They kind of just sit in particular positions and vibrate a little bit. In a liquid, the molecules or atoms can slide past each other. That's called kinetic energy. And in a gas, the molecules or elements can move past each other even more rapidly. Okay. And any element or molecule can exist in any of those three states. Okay. An example would be a water molecule, right? Water can be a liquid, or it can be a solid like ice, or it can be a gas like steam, or like clouds, or water vapor. Okay. So what determines what state of matter you're in is a combination of temperature and pressure. Okay. Usually the higher the temperature and the less the pressure, then you're going to shift from a solid through a liquid all the way to a gas. Okay. That's the way it is. Energy is just the ability to do work, and energy comes in a lot of different forms. Okay. There's mechanical energy, where things physically move from one place to another through applied force. Okay. There's electrical energy, which is the movement of charged particles from one location to another. We call that current. Okay. There's potential energy, like the tension in a bowstring, like you're looking at here, right? This guy shoots an arrow.
Energy is the capacity to perform work. Potential energy is energy that is stored. Kinetic energy is the energy of motion. Energy is neither created nor destroyed. but converted from one form to another. This property is called the conservation of energy. The bow and arrow start out with low potential energy. As the archer's arm pulls back the string, kinetic energy from the arm's motion is converted to potential energy in the tense bowstring and arrow. When the bowstring is released, the stored potential energy is converted into the kinetic energy of the moving arrow. When the arrow hits the target, its motion ceases. If energy is neither created nor destroyed, where did the energy of the flying arrow go? Let's rewind and look at kinetic energy in more detail. When energy is converted from potential energy to kinetic energy, some of the energy can be used to do work, but some energy ends up as heat, a type of kinetic energy. Heat is the random motion of atoms and molecules. As the arrow flies through the air, heat is generated by friction between the arrow and air molecules. When the arrow strikes the target, all the energy becomes heat energy. The heat energy is rapidly transferred into the air and spreads out. Heat energy is a very disordered kind of energy. It has the highest amount of entropy, or disorder, of any kind of energy. Where do our muscles get energy to perform work, such as pulling back a bowstring? Our bodies use the chemical energy from food to perform work. Chemical energy is a form of potential energy. When your body breaks down food molecules, the stored potential energy from food can be converted to kinetic energy. The stored chemical energy in food is released in your muscle cells during the process of cellular respiration. Using oxygen, cellular respiration converts chemical energy from food to another form of chemical energy called ATP. Water, H2O, and carbon dioxide, CO2, are byproducts of cellular respiration. The potential energy of ATP can be converted to kinetic energy. Some of the kinetic energy is used to do useful work, such as pulling back a bowstring, but the heat energy that is generated cannot be used to do work.
So every time something happens in the universe, right, something moves or electrical current is produced or work is done in some form, the heat that's given off goes off into the universe, and then it makes the universe more random, and that's called entropy. And there's two rules that govern the whole universe, and they're called the first and second laws of thermodynamics, and they're pretty easy. The first law of thermodynamics says that energy and matter can't be created or destroyed. They can be transformed, but there's no way to make something appear out of nowhere, and there's no way to make something disappear, okay? All you're doing is changing the way that it exists, okay? You can turn matter into energy, okay? And there's an equation for that, E equals mc squared, where E is energy and m is the mass of the matter, and c is the speed of light, okay? And that means that if you take a tiny bit of matter and turn it into energy, you get a lot of energy out, okay? But again, it's just another way of saying there's only so much stuff in the universe, and that's all we have, okay? And then the second law of thermodynamics just states that if we consider any system, like the water in a glass or the air in the room or a drop of food coloring in a glass of water, that if we wait, what will happen is that it will try to find the lowest energy state, which means the arrangement of those things that takes the least amount of energy to maintain, okay? And so that's why, for instance, if you put a drop of food coloring in a glass of water and just wait, or if you put powdered Kool-Aid into water and just wait, what will happen eventually is that the molecules of the dye or the Kool-Aid will eventually disperse throughout the entire liquid without you doing anything, okay? And so generally, what's going to happen in terms of chemistry is that things are going to obey those two laws, right? We're not going to create or destroy any matter or energy, and we're not going to try and set things up so that it takes a lot of energy to maintain a system, okay? different forms of energy, right? All over the place, all around you all the time, right? Chemical energy is in the connections between atoms that hold molecules together, okay? Electrical energy is the movement of charged particles like electrons or protons. We'll learn about those in a second. And mechanical energy is force that moves matter from one place to another. And then there's electromagnetic energy in the form of things like light and UV and X-rays and radio waves, okay? And it's an unusual kind of energy because it has an electrical part to it and a magnetic part to it. And it's able to move through a vacuum, meaning it can go through empty space. So that's a little bit unusual. And there's still a lot of things about electromagnetic energy we don't fully understand, okay? We can't see it, but we can see its effects, okay? Whereas a lot of these other forms of energy we can see. Energy can be converted from one form to another, okay? But when that happens, you lose a little bit as heat, and that goes off and randomizes the universe, okay? Just like the guy shooting the arrow into the target, right? Where did the energy go? Well, some of the energy was used to move the arrow to the target. Some of the energy was released as sound and pressure, and the rest was lost as heat. And so the energy didn't disappear, it just changed, okay? Matter is made up of elements, all right? And elements basically are components, matter in the universe that cannot be broken into simpler substances by chemical means, okay? Each element has unique properties that we can pick up with instrumentation or with our senses. And then they have chemical properties which determine how they interact with each other, how they hook up, okay? The atom is the smallest unit of an element, okay? It's the tiniest piece of an element that can't be broken down any further, okay? So it still has the chemical and the physical properties of a bigger chunk of that element, all right? But we can't go any tinier than the atom, all right? And this actually comes from an ancient Greek named Democritus, who was sitting around one day with nothing to do, and he was staring at a boulder, and he thought if you split that boulder in half, you'd have two tinier boulders that still had the properties of the original, and if you continued, you'd have four even tinier boulders that still had the properties of the original. But he reasoned that eventually you'd get to a point where you couldn't get any smaller, and he called that particle the atom. And it comes from the Greek a meaning not, and tomos meaning divisible, not divisible, right? And that's kind of the working definition of the atom that we have today, okay? An atomic symbol is just chemical shorthand for an element, okay? You can see some symbols here, C for carbon, H for hydrogen, and so on, okay? These make up most of our body mass, right? And then there's some other elements that make up about 4% of our body mass, but they're still very important because without them, we wouldn't be able to function. Example, all right, calcium is important in building bone, and it's also important in muscle contraction and nerve function, okay? Phosphorus is part of the cell membrane and part of DNA and RNA, which are information molecules in the body, okay? And it's also used to regulate cellular activity. Potassium is an important part of the electrolytes in our body, which are important because they allow the conduction of current, and they also allow the cells in our body to use that current to do work, okay? And it's also important in determining where water goes in the body. Sulfur is important. It's part of the structure of molecules called proteins that we'll learn about a little bit later. Sodium is also part of our electrolytes and plays a role in muscle contraction and nerve function and the movement of water in the body. Same with chlorine. Magnesium is important for the production of energy. Iodine is critical for the production of certain hormones in the body, and iron is important for energy production and also to move oxygen around the body. Okay, so if I were to like snap my fingers and take those elements out of your body in one shot, you'd fall over dead, right? Wouldn't be able to function. So even though they don't make up much of our weight, they're still very important. We get them in our diet, right? Trace elements come in small amounts. 11 elements make up a very tiny amount of our body mass, but they're still critical. Chromium, copper, fluorine, manganese, zinc, and so on. Okay. The model of the atom that we use is shown here. There's two versions, right? There's what we call the planetary model and the orbital model. Okay. And in the planetary model, we have particles that are called protons and neutrons, and they sit in the middle of the atom in an area called the nucleus. And then the electrons zip around the nucleus at very high speeds, okay, and have a negative electrical charge. In fact, they move at the fastest speed anything can move, which is the speed of light. Okay, so that's really fast. The orbital model has electrons outside the nucleus in a three-dimensional region, okay? These orbitals have different shapes. Some of them are shaped like a sphere. Some are shaped like a dumbbell. Some are shaped like rings, okay? It all depends on which orbital we're talking about. And again, the protons with the positive electrical charge, the electrons with a negative electrical charge, and the neutrons with no electrical charge, just like in the planetary model, okay? Most of the mass of an atom is in its nucleus, okay? This model, though, is a little puzzling, right? Because if we look at that model and we think about it for a minute, some of the things in it kind of don't make sense, right? If the middle of the atom has a positive charge and the things zipping around the outside of the atom have a negative charge, then you might wonder why the atom doesn't collapse or explode. But it doesn't. And the answer as to why that is, which comes to us from many, many years of research, believe it or not, is we don't know, okay? What these are models. And all a model is our best guess at the way something works, according to what we've known so far. And models change all the time. And sometimes we have to throw models away because of new things that we learn, or sometimes we have to modify the models that we have, okay? So what we do with the model is that we take what the model gives us, and then as we learn new things, we modify the model, okay? If we look at the structure of some of the different elements, the atoms of some of the different elements, what you see, right, with the lightest element, hydrogen, you have one proton in the nucleus and one electron in what we call the first orbital. The next heaviest element, which is helium, has two electrons in the first orbital, two protons in the nucleus, and two neutrons in the nucleus. And then lithium, you've got three electrons outside with two in the first orbital and one in the second. And then you've got three protons and four neutrons, okay? So what you notice about this is that the number of positively charged particles, which is represented by a number called the atomic number, okay? So the atomic number for hydrogen is 1, atomic number for helium is 2, and for lithium is 3, okay? Is always going to be the same as the number of electrons. So the atom is always electrically neutral, meaning it doesn't have an electrical charge on it in its normal state, okay? The other thing you notice about it is that there are certain rules that determine how many electrons can be in a particular orbital, okay? For instance, in the first orbital, the one closest to the nucleus, you can have a maximum of 2 electrons. In the next orbital, you can have 8. And in the next orbital, you can have 17, but you can be stable at 8. And by stable, I mean low energy. Again, it's that second law of thermodynamics, okay? So, you can see here the periodic table, okay? And believe it or not, this is a list of all the elements in the universe. It's on one page, okay? Which is pretty amazing when you think that the universe is infinitely large. But notice some of the different colors here, okay? Over here, you have a special group of elements that don't do any chemistry. They don't hook up with any other elements. They're happy the way they are, and they're found in their pure states in nature. And we call those the noble elements. They don't do any chemistry. What that tells us about those elements is that they must be low energy because they don't perform any chemical reactions. And what do we know about the universe? Everything wants to be in a low energy state. So look at all the other elements, right? None of the other elements do that. All these other elements perform chemical reactions, which means that what must be driving chemistry, which is nothing more than the making and breaking of chemical bonds, is the attempt on the part of all these other elements to be like the elements in this column, okay? So the columns are called groups and the rows are called periods, okay? Heavy goes from left to right and top to bottom, so the heaviest stuff is down here and the lightest stuff is up here, okay? And then these different colors, right? These guys in gray are called non-metals, okay? Everybody else in green and yellow and sort of copper and silver, those are metals, all right? And then these are special. These are the noble elements, all right? So what are some of the general rules about chemistry regarding these different types of elements? Well, when non-metals react with metals, they tend to form what are called ionic bonds, in which the metal is going to lose electrons and get a positive charge, and the non-metal will gain an electron and get a negative charge, and then they'll attract each other because that's what opposite charges do, okay? Most of those compounds are called salts, right? When non-metals react with each other, these guys over here, they tend to form covalent bonds, meaning that a pair of electrons, or maybe sometimes more than one pair, are shared between two atoms, and that's what holds them together. Covalent bonds tend to be stronger than ionic bonds, okay? When metals react with other metals, they form metallic bonds, and they form things called alloys, and those are beyond the scope of our course, okay? So that's the periodic table. Now, these numbers are just telling you the atomic number, right? The number of protons in hydrogen's nucleus is 1. For boron, it's 5. For carbon, it's 6. 7 for nitrogen, 8 for oxygen, and so on, okay? And you'll also notice these numbers at the tops of these columns. Those are called group numbers, and all they're telling you is the number of electrons in the outer shell of the atom, okay? So everybody in this column has 1 electron in its outer shell. Everybody here has 2. Everybody here 3, 4, 5, and so on, okay? Why do we care about the electrons in the outer shell so much? Because that's where the action is. That's where the chemistry takes place. That's where chemical bonds are made and broken. And that's because those electrons have the most energy, okay? So those are just some of the basic rules. And where is carbon in all this? We were talking about organic molecules earlier. It's right there, right? Atomic number 6, 6 protons in the nucleus, 6 electrons outside the nucleus, with 2 in the first shell and 4 in the outer shell, okay? So for the chemistry that we're going to learn in this class, all right, we're mostly interested in what happens with, let's see here, isotopes, go through that. We're mostly concerned with what happens with the first and the second shell, okay? Because the other elements, I mean, we'll run into them, but not real frequently, okay? Remember I told you about the noble elements, right? Well, there's helium with a full outer shell with 2 in that first orbital, right? And then there's neon with 8, 2, 4, 6, 8, right? Again, found in their pure states in nature. The other elements, right, are trying to get a full outer shell. So how do they do that? They do that by either sharing or losing or gaining electrons, okay? So hydrogen with 1 in its outer shell could pick 1 up to fill it. Carbon with 4 in its outer shell could pick 4 up to fill that shell. Remember, that shell sleeps a total of 8, right? Sodium, when it reacts with a nonmetal, will kick out this electron, and then underneath it is a full shell. So even though it gets a charge, it's still happier in terms of energy because that shell down there is full. Where does the other electron go? It goes to some other element, usually a nonmetal. Oxygen, right? 2, 4, 6, so it can pick up 2 electrons, okay? So the 3 major kinds of bonds are ionic, covalent, and hydrogen bonds. These 2 are within a molecule. Hydrogen bonding is something a little different. We'll get into that a little bit later, okay? Ionic bonds happen when an electron moves from one element to another, okay? So we transfer an electron from a metal to a nonmetal, okay? The metal has a positive charge and is called a cation, and the nonmetal gets a negative charge and it's called an anion. The way I remember that is that the T in cation looks like a plus symbol. So I remember cation is positive, okay? And so what happens is that they get held together because of opposite charges, right? Here's sodium and chlorine, right? Sodium's got 1 electron in that outer shell. Chlorine has 7, right? So what happens when they get near each other? The sodium will punt this guy over to the chlorine. This will take on a positive charge. This will take on a negative charge. And that's what holds them together. Now, let me tell you a little bit about these elements, okay? Sodium metal is very dangerous, okay? If I were to bring sodium into ATA, I would have to carry it in a glass tank under kerosene, because when it comes into contact with the water and the air, it bursts into flames. It's actually kind of cool, okay? Chlorine, I don't know if you've ever been around a pool when it's being chlorinated, will bleach your skin and bleach your mucous membranes and burn your eyes, okay? So it's very corrosive, okay? But when you put them together, guess what you make? You make sodium chloride. That's table salt. That's what you put on your French fries. And you can eat that. So why can you take 2 dangerous things and turn them into something that you can eat? And the answer is because the electrons have changed where they are. And that's changed the chemical properties of the compound. Okay? If you look at a salt crystal under a magnifying glass, you'll find that it's a cube. And that cube is actually made up of a bunch of little cubes all stacked together. And you'll notice that if you look at the way that the cube is arranged, that the negative charges and the positive charges are all interspaced with each other. And that's so they can hold each other together in that shape. And that obeys the second law of thermodynamics that says that we always try to arrange things in the lowest energy way, right? We tried to make all the negative charges be on one side of the cube and all the positives be on the other. They would push away from each other, and we would have to use a lot of energy to make them hold that shape. So that's not what they do. They end up getting together like this, okay? Covalent bonds are different. Okay, and in a covalent bond, what happens is that you share electrons between two atoms. Now, sometimes the sharing is totally equal, okay, meaning that the pair of electrons spends just as much time with atom number 1 as it does with atom number 2. We call that a nonpolar covalent bond. And sometimes it's unequal, meaning it spends more time with atom number 1 than atom number 2. And we call that a polar covalent bond. Bonds between carbon and hydrogen, okay, are nonpolar covalent bonds. Bonds between identical nonmetals are nonpolar covalent bonds. Everything else that's a covalent bond is going to have some polarity to it, meaning that the molecule is going to have a slightly positive and a slightly negative end to it. So there's a rule that tells us about nonpolar and polar compounds, right? They like to be with their own type, okay? Nonpolar molecules like to be with other nonpolar molecules, and polar molecules like to be with either charged or polar molecules. Another way of saying that is that like dissolves like. Things that are similar mix easy, right? An example of when this doesn't work is oil and water, right? You know that if you take some Wesson oil and you put it in a glass of water, that even if you stir it, it's not going to stay mixed up, right? The oil will separate on the top and the water will be on the bottom. Now, why is that? Because that's the low energy state, right? The nonpolar stuff, which is the oil, which contains mostly carbon-hydrogen bonds, likes to be with itself. And the water, which has a negative and a positive end to it, likes to be with itself. And so if you just wait after you stir, everything will separate. It's the same thing with a bottle of oil and vinegar dressing, Italian salad dressing in the store. When you take it off the shelf, the oil's on the top and everything else is on the bottom, right? That's the low energy state. But if you take that bottle and you shake it up, then you make a temporary mixture called an emulsion. And that is because you added energy to the system by shaking it, right? And so you created a high energy state. But if you wait, put the bottle down and just wait, what happens? The oil will separate again, okay? And that's the second law of thermodynamics, okay? Some more examples of nonpolar covalent bonds are here, right? You've got nitrogen that can form 3 covalent bonds when it gets together with another nitrogen. Remember, 5 in the outer shell, it can pick up 3. And so if we count here, look at the outer shells of both atoms, right? 1, 2, 4, 6, 8. So that nitrogen atom's happy. 1, 2, 4, 6, 8. So that nitrogen atom is happy. By happy, I mean low energy, right? So that's a stable compound. That's not going to do anything, okay? Oxygen, right? 6 in the outer shell can pick up 2, so it can form a double covalent bond. 2, 3, 4, 6, 8. Right there. 2, 3, 4, 6, 8. Right there, okay? So everybody's happy. These are nonpolar because the pull on the electrons in the chemical bond is equal from both atoms, like a tug of war, right? Both teams are equal strength. And that same condition exists with carbon and hydrogen, okay? When you have a covalent bond between an atom that has more tug on the electrons than another atom, you're going to create a polar covalent bond, meaning that one end of the connection between the two atoms is going to be a little bit negative, and the other end is going to be a little bit positive, okay? So if we go back to the periodic table, the electronegative atoms, which are the ones that are going to tend to pull electrons towards them, where would they be? Well, they're going to be to the right of carbon over here. They're in this area, okay? And everything electropositive, meaning it tends to give up or have less hold on the electrons, that's going to be to the left of carbon, even out to the metals and all. Okay, so that's just sort of a guidepost. So if you look at an organic compound and you see a nitrogen or an oxygen or a chlorine or a sulfur or whatever, you can assume that that's a polar organic compound, okay, which means it's going to try to get with other polar compounds or get with charged compounds. If you don't see very many of these, then it's a nonpolar compound. If it's mostly carbon and hydrogen, then it's a nonpolar compound. It wants to be with other nonpolar things, okay? So that's how that works. And that's, again, that's just the second law of thermodynamics doing its job, okay? So the electronegative atoms, we know where they are. The electropositive atoms, we know where they are, okay? So what about water? Water has polar covalent bonds in it, right? The oxygen is electronegative, the hydrogen is electropositive, and so even though they form a covalent bond with each hydrogen, the oxygen atom spends more time with the electrons, and so it takes on a slight negative charge, and the hydrogens take on a slight positive charge, okay? So in terms of polarity, right, there's a continuum, right? Ionic bonds are the most polar because they have total charge separation. Then you got polar covalent bonds, and finally, nonpolar covalent bonds, no separation of charge, right? And so that allows water to have certain properties, okay? And those properties include things like surface tension, where the water has a slight upward force to it that can support the weight of something like a water strider, you can see here, because the water is more attracted to itself than the air above it, okay? It's also responsible for capillary action, like when you spill something in the kitchen and you get a towel out and the fluid wicks up into the towel, right? Why does that happen? Well, because the water is polar, the components of the towel, which are cellulose, are polar, and so they attract each other, okay? That's how you get water up to the top of a tall tree, right? The tree is made of wood. The wood is the same thing that your towel is made of. The water wicks up into the wood. There's a little bit of upward pull because the leaves have little openings in the bottom that allow them to lose water vapor. So that provides a little extra draw. And you can get the water all the way to the top of a tall tree, okay? And that's also why when water freezes, that it expands in volume, right? Because when you've got liquid water, right, you have a situation in which the molecules are sliding past each other, okay? But when the water has to become a solid because the temperature drops, you have to arrange the molecules so that the negatives are near the positives and the positives are near the negatives, and that takes up more space. And that makes the ice less dense than the water. And that's why ice cubes float in a glass of water. And you all knew that already, but that's why, okay? That's also why if you forget and leave something in your car in January with the trunk closed, like a 6-pack of Coke or juice or whatever, and you forget about it, it freezes overnight, you come back the next morning and open the trunk, you're going to have a big mess because the cans of the bottles will all have split open and all that stuff goes all over your trunk, okay? And that's, again, just obeying that second law of thermodynamics, all right? So bump out of here, okay? And I'll send this to you as well. It's part of a bigger presentation. And then let's bump back into where we were talking about organic compounds, right? So this makes more sense to you, okay? So we talked about organic compounds and what they can do and why, okay? They're unique to living systems. They include carbohydrates, lipids, proteins, and nucleic acids, okay? A lot of them are polymers, meaning that they are repeating chemical units hooked one after the other like links in a chain, okay? Proteins are polymers, nucleic acids are polymers, complex carbohydrates are polymers. they're made by something called dehydration synthesis, which means that you pull out the equivalent of a water molecule to create a new chemical bond between two smaller things and make a bigger thing. And they're broken down by hydrolysis. Hydrolysis means using water to split, hydro water and lysis split, and that makes a big thing break apart, okay? So these reactions, the building up reactions, are called anabolic reactions, and they require energy to happen. And that energy is in the form of a molecule called ATP. We'll talk a little bit about that later. And the breakdown reactions release energy that can be captured, and then the cells in our body can take that energy and give it to ATP so that we can use it to do work, okay? So all carbohydrates, actually, let me correct this real quick because I want this to be right here. It should be CH2O. There we go. So all carbohydrates have a chemical ratio, CH2O, where the number of carbons and oxygens are the same in the carbohydrate, and there's twice the number of hydrogens. So if you had a carbohydrate that had 6 carbons in it, the chemical formula would be 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. And we would write that C6 with the little 6 down here, H12, the little 12 down here, O6, okay? That's all that means, which means there's a lot of oxygen in carbohydrates, which means that they're polar, which means they like to mix with water or with other polar things, okay? Average minimum carbs needed to make the brain work. The nervous system only runs on carbohydrate for energy. That's its only fuel, whereas other tissues can run on other things, is 130 grams a day. Average carbohydrate intake in the US is about almost over double that, okay, between men 20 years and older, and 256 in women of the same age range, okay? The difference is due to size. Men tend to be bigger. The AMDR, acceptable macronutrient distribution range, is between 45 to 65% of your calories, okay? So how do you work that? Well, the number of calories needed to maintain your body weight is about 2,000 calories a day. Calories is just a measurement of energy, okay? And what they're saying is that, let's take the low end, let's say 45% of that should be part of that 2,000 calories, which means you're going to have a little under 1,000 calories in order to meet those recommendations, okay? Why not more than, say, 65%? Well, because then you're likely to gain weight and tend towards obesity, okay? And if you have less than 45%, you're not going to have enough carbohydrate in your system to let your nervous system work, okay? So what's their role in the body? Energy for cellular work, okay? And regulate protein and fat metabolism, which is a broad term meaning they're building up and they're breaking down, okay? So the catabolic and the anabolic reactions together make up our metabolism. They're important for normal heart and nervous system function, okay? Carbohydrates are classified according to what they look like chemically, okay? Monosaccharides are single ring sugars. Examples include glucose, fructose, and galactose. Disaccharides are double rings, 2 single rings hooked together. Examples include lactose and sucrose. And polysaccharides are longer chains, so 3 or more. And those include things like starch and fiber and glycogen, okay? There's other types of polysaccharides too. The general chemical formula to build them up and break them down is shown here, right? This is a dehydration synthesis reaction. So you've got an OH group, a hydroxyl group hanging off of each sugar, and you can using a tool called an enzyme, remove the essential components of a water molecule and spit it out and form a new chemical bond between them. So that's like hooking the links in the chain together. And that's a dehydration synthesis reaction because you're removing water, dehydration, okay? And that consumes energy to go. It doesn't happen all by itself, okay? So usually that energy comes from a source like ATP, okay? Hydrolysis reaction is sort of the reverse, okay? An enzyme will take a water molecule and use that to cut this connection, and now you'll have two monomers that are released. And that releases energy that can be used to do other things. And this is just sort of drawing it out with a sugar, right? This is a representation of a glucose and a fructose molecule. The way this works is that each little bend in the ring represents a carbon atom, okay? And then the groups hanging off the sides are shown here. Remove the equivalent of a water molecule, and you form this disaccharide called sucrose. This is table sugar. This is what you put in your coffee, okay? And if we break this down, which is what happens in our body, we use water and a tool called an enzyme to crack this bond and generate these two monosaccharides. And that's what we're able to absorb into our bloodstream, and then from there to our liver, and then from our liver to the rest of our body, okay? So those are the carbohydrates. That's what they contain, right? There's that formula where N is the number of carbons in the carbohydrate. The three classes, monosaccharides, disaccharides, and polysaccharides, and what they're for. Mostly fuel, but they're also structural components in the body. They're part of the structure of RNA and DNA, which are the information molecules in the body. And they're also important in what we call the glycocalyx, which is a collection of sugars on the surface of our cells that serves as an ID tag for our immune system so that it knows that those cells and tissues are healthy and so it doesn't attack them, okay? This is from your textbook showing you sources of these different types of carbohydrates and what they're for, okay? So this is table 1.1. Okay. Monosaccharides, again, the formula we've already talked about, where N is the number of carbon atoms. These are the monomer units of carbohydrates. Important monosaccharides in the body include ribose and deoxyribose. You can see those down here, okay? Those are part of the backbone of DNA and RNA, okay? And then hexose sugars like glucose and fructose and galactose, okay? What happens in the digestive system is that glucose passes straight into the blood, and then fructose and galactose get chemically rearranged into glucose, and then they go into the blood, okay? And then from there, they go to the liver, where they may be stored as glycogen or fat for a while. And then when we need them, they'll be released from the glycogen and fat by the liver and put into the blood as glucose. And then that'll go from the blood to all the cells in our body so they can use it for energy, okay? Disaccharides are just double sugars, okay? They're too big to pass through the digestive system into the blood by themselves, so they have to be modified. They have to be split into monosaccharides. Important ones include maltose and sucrose and lactose, okay? There's a look at how they're made.
Sometimes organisms link sugar molecules in pairs to form disaccharides. Here are several examples. Plants make sucrose by joining glucose and fructose. Sucrose circulates in plant sap, and we obtain it from sugarcane and sugar beets and use it as table sugar. Lactose is formed by joining galactose and glucose. Lactose is the disaccharide that gives milk its sweet taste. Maltose consists of two linked glucose molecules. Digestion of starch in a sprouting seed or in the intestine of an animal produces this disaccharide.
So I don't know if anybody in the class is lactose intolerant, but if you are, you lack the ability to break down lactose in dairy and use it for energy. So what happens in people that are lactose intolerant is that the lactose gets all the way to the colon, where the bacteria that live there, like E. coli, use it for energy and produce large amounts of gas, and that causes pain and distension and irregularity, okay? And the fix for this is to either avoid lactose or to take the enzyme in the form of a pill so that you can break the lactose down and use it for energy, okay? Some people have lactose intolerance and some people don't. Polysaccharides are just longer chains, okay? And so here's how they're made and broken down.
Polysaccharides are polymers, long chains consisting of hundreds to thousands of linked monosaccharides.
So you can see some examples here, right? Starch and glycogen we can eat and use for fuel. Cellulose has another name. We call that wood or fiber. And we're not able to break that down because we don't have the right tool to split that particular kind of bond, okay? It's like kind of like not having the right key for a particular lock. And so what happens when we eat cellulose is it passes right through our body and out the other end like fiber does. Now, it does provide fuel for the bacteria that live in our colon, okay, because they have the tools to break these bonds, right? But not for us. So one of the ways you can cut your calorie content in your diet is to eat stuff that's very high in fiber, okay? Glycogen is animal starch, and that's made in liver and in muscle, and we can digest that. And starch, of course, is what we find in things like rice and potatoes, and it's a fuel storage mode for plants, okay? Our main fuel storage mode in our body is something called fat, okay, or triglycerides. The liver has as one of its jobs the conversion of fructose and galactose into glucose, which is then released into the blood. This elevates our blood sugar levels and causes insulin to be generated by the pancreas. And the insulin serves as a signal to the tissues in our body to take the sugar out of the blood and to use it for fuel, okay? It also serves as a signal to the liver to make more glycogen and more fat, okay? The body digests 95% of the starch you eat between 1 to 4 hours after you eat it. Digestion occurs mainly in the small intestine using pancreatic amylase, which is, again, a tool called an enzyme that helps to break that molecule down into smaller pieces. And that reduces the complex carbohydrates into disaccharides. And then there are other enzymes, other tools, that break the disaccharides down into monosaccharides, and then we can pass that into the blood, and then from there it goes to the liver, okay? Glycogen is the stored carbohydrate energy source in the liver and in our muscles, and it's sort of a quick energy storage that gets used up real fast if we're very active, okay? But it's not the main way that we store energy. The main way that we store energy in our body is by the storage of fat, okay? To maintain your blood sugar levels between meals, glucose is released by the breakdown of glycogen in the liver, okay? And that is that happens as a result of the effect of a hormone that's made by the pancreas called glucagon, okay? So the pancreas makes hormones that both lower blood sugar levels, those are called hypoglycemic hormones, and raise blood sugar levels, and that's called a hyperglycemic hormone. Okay? Fiber is a carbohydrate that has no calorie value for us. Okay. Examples include pectin, gum, cellulose, and other oligosaccharides. And the reason that we can't use it for fuel is because we don't have the proper tool to crack the chemical bonds that hold those molecules together so they don't pass into our bloodstream. Fiber is critical for remaining regular, okay? The way that works is that when the fiber makes it to our colon, it draws water into our stool and it makes it easier to pass, okay? And that's why as we get older and the movement of food through our digestive system slows down, we tend to get more constipated. And one of the ways we avoid the problem of constipation is to increase the fiber in our diet, which means we either take a fiber supplement or we increase the fruits and vegetables in our diet so that we stay regular. Studies show that fiber can lower cholesterol and reduce intestinal cancer. It sort of acts like a scrub brush in a way to get some of the stuff that might promote cancer out of our digestive system more easily. Total fiber recommendations, 25 grams a day for women and 38 for men. And that's, again, because of the size difference, okay? Men are just bigger, okay? All right, let's take a break, and we'll come back at 11:50, all right?
Good morning, Mr. Commerce. Shanique was here.
Okay, I got her. I'll put her in.
Thank you.
Mm-hmm.
Quick question, Mr. Commerce. Did you send us already our homework?
I did. Did that this
Okay,
morning.
because I didn't see it. I had to go back to the email that you sent me last week so I could connect the class today.
Check both the emails. It should be in there. I sent it to your regular email
All right.
and to your ATA. It's also posted on the
Okay.
on your student portal, so you can download it from there too.
All right. Thank you.
Yeah, you're welcome.
Okay, one more crazy question.
That's so? Yeah.
How early can I turn in my disease report?
As early as you would like. Doesn't matter. If you want to work ahead, that's
okay,
fine.
great.
Yeah. I have no
Yeah,
problem with
I've
people working ahead.
Yes, sir. I've been making moves happen.
Okay, that's good. That's good.
Okay. Okay. I just wanted to make sure I can turn that in as soon as I finish it.
Sure, sure.
Okay.
Yeah, you good. All right.
Mr. Converse,
Yes, ma'am.
is this what the homework look like? Is it
Uh,
under student outline?
well, it's so I sent it to you in an email as a PDF and as a Word document.
It say Nutrition 100 and say Chapter 1.
Yeah, that's the that's your notes. That was from chapter 1 was from last week, I think. Intro, right?
It's the
And
email you just sent me though.
yeah, and there should be a second one that you got today, and that will have today's homework and today's lecture notes too.
That's the one I just clicked on. I don't know which one the homework. You got syllabus, Chapter 2, carbs, nutrition.
There we go. There you go. That's it.
That's the outline. That's what you just went over today.
Yeah, but there should be homework in there too. There should be a Word document that's fats and carbs. this homework.
Word document. Yeah, that's the Word document. That's the one I was just asking you about when I first asked.
Yeah, that's homework. Yeah, the Word document, that's homework.
Okay,
The PDFs, those are like notes.
gotcha.
Yeah. Okay. But that. boys. Mm-hmm. It's pretty cold. Are you the dogs? All right, y'all. We're back. Everybody here?
I'm back.
Back? Okay. All right. So our next topic are lipids. Okay. Now lipids have more calories in them than any other of the macromolecules in our diet, right? More than protein, more than carbohydrate. And the reason is that they have more calories per gram. And the reason they have more calories per gram is because they have more carbon hydrogen bonds in the molecule than either a carbohydrate or a protein does. Okay, all you have to do to determine the relative calorie content of an organic molecule, one that has carbon and hydrogen in it, is to count the number of carbon hydrogen bonds. And the more carbon hydrogen bonds you count, the more calories are in there, which means there's more energy in there. Okay. So the fats are divided into triglycerides, which are made up of a carbohydrate called glycerol and are attached to molecules called fatty acids. There's 3 of them in a triglyceride. Phospholipids, which are made from triglycerides by removing a fatty acid and adding a phosphate group. And sterols, which are an alcohol that has a carbon hydrogen ring system attached to it that we'll take a look at in just a minute. Okay. So when we talk about triglycerides, we can look at the calorie content of saturated and unsaturated triglycerides. Saturated triglycerides are going to have all saturated fatty acids in them, and an unsaturated triglyceride will have 1 or more unsaturated fatty acids. Now, what does saturated mean? Saturated just means that there's the maximum number of carbon hydrogen bonds in that fatty acid tail that you can have, which means there's the maximum number of calories in there. Well, an unsaturated fatty acid, if you look at it, some of the connections between the carbon atoms are going to be double bonds. And when that happens, that cuts down on the number of carbon hydrogen bonds, and that cuts down on the number of calories. Okay, so that's why we say that if you cook with unsaturated or polyunsaturated fatty acids, that you're cooking heart healthy, because what you're doing there is you're cutting your calorie content. So it's always better, for instance, to fry something in, say, vegetable oil than it is to fry it in Crisco, even though it tastes better in Crisco, and I know it does. The vegetable oil is better for your heart because it's going to cut down on your calorie intake, which is going to cut down on the amount of triglyceride and cholesterol in your blood. Okay, you get a lot of cholesterol and triglyceride in your blood, that's going to push you towards a condition called atherosclerosis, in which you get these plaques that accumulate on your arteries that cause your blood pressure to go up and make it more likely that you're going to have a stroke or a heart attack. Okay. Now, a little bit of insight into why we like to eat things that are high in calories, okay, like sweet stuff and like stuff that has a lot of saturated fat in it. Those high calorie targets taste good to us because way back when we were all living in caves, right, we didn't eat regularly. Okay, we ate whatever wandered past the cave, right? We'd run out and kill it and eat it. Okay, and generally, if we wanted to eat it, it would taste better to us if it was a high calorie target, because that meant we were likely to survive longer. Okay, if you didn't like to eat high calorie food back in the day, then you weren't going to live long enough to reproduce. You weren't going to live long enough to have kids. which means you weren't going to pass that trait on to your children, which means they're less likely to survive. Okay, so we're set up by evolution to like high calorie stuff. But what happened was that man invented farming, okay, and he was able to learn how to grow crops that produced a lot of food and thus a lot of calories, and raise animals that did the same thing. And as a result, he ended up with more calories than he could eat. And so what we did with those extra calories, those crops and that meat and all that, was we started to trade with other small groups, right? And that's what started commerce, and that's kind of what began civilization, cities and towns and all that stuff, right? You have a lot of this, I have a lot of that, let's trade, and then everybody has what they need, okay? The consequence of that now is that we have so many calories, and it's so easy to eat so many calories, that obesity is the main health problem in Western countries. It's weird, it's real simple to take in a lot of calories without realizing it, okay? And I always use the example of combos, those little pretzel snacks that have the filling in the middle that you can get in the vending machine. And a serving of combos is 200 calories. And since 2,000 calories a day is your ceiling to maintain your weight, you figure, well, I can eat this bag of combos and I'm fine. But what you don't realize is that a serving of combos is defined as 2 combos. 2 of those little pretzel things, that's it. So in that bag that you got, that's probably half your calories for the day. So if you eat 2 of those little bags of combos, you can't eat the rest of the day unless you want to take in extra calories and gain weight. It's kind of surprising, but that's why it's easy to gain weight if you're not careful. You have to be aware of the calories in the container, right? And we'll get into reading food labels a little bit later in the course, okay? A lot of those snack foods, by the way, are made with saturated fatty acids, which are high calorie. You've probably heard of trans fats. They're a type of saturated fatty acid that improves the shelf life of things like combos and other snacks, right? But also raises the calorie level, okay? So we're looking at fats. The first class are triglycerides, right? And they're made up of 3 fatty acids and a backbone of glycerol. They tend not to dissolve in water very well because that carbon-hydrogen part of the molecule, which you can see here, is nonpolar, right? So it doesn't mix well with water. While this part may be able to combine with water a little bit because there's some oxygen atoms here, right? So we call this molecule amphiphatic, meaning it's got a greasy end and it's got a non-greasy end, okay? Things that are made from triglycerides include phospholipids, okay? And you can also have lipid molecules that have carbohydrates attached to them in some cases. Then there are steroids, which are made from a different type of lipid, and eicosanoids, which are made from fatty acids. So let's take a look at lipid.
Butter, lard, margarine, and salad oil are composed of lipids called fats. To make a fat molecule, 3 fatty acids bind to a molecule of glycerol. For this reason, fat molecules are technically called triglycerides. Fat molecules do not mix with water because they have 3 long hydrocarbon tails. Cells use fats for energy storage because the tails hold more potential energy than other biological molecules.
So triglycerides are called fats when they're solids and oils when they're liquid. At room temperature, a saturated fat and a saturated triglyceride are going to be a solid. They think of things like butter and Crisco, okay? And at room temperature, an unsaturated fat or an unsaturated triglyceride is going to be a liquid. And the reason for that is that the double bonds in the fatty acid tail means that the tails don't stack quite as easily, which means they move more, which means they're going to be more like a liquid. Okay. The main functions: energy storage, insulation, protection. In our body, our fat helps to hold in our body heat. It helps to pad and protect our internal organs. Okay. But it also is our major body's pantry. This is where we store a lot of our extra energy, which is why if you burn calories and eat less, you lose body fat. Okay, that's how exercise and diet work. So you cut down on the amount of calories going in, you burn more of the calories that you store, you lose weight. Okay, now an important point here is, why does the body use triglyceride as our energy storage mechanism instead of something like glycogen? And the reason is that it takes up less physical space. And that's because triglyceride likes to associate with itself and not so much with water, which means that it doesn't take up as much volume. So you can pack a lot of calories into a tiny volume, and as a result have more than enough energy to allow you to continue to be active and maintain your blood sugar levels when you're not eating. Okay. So it's a good thing, right? And that's also an important point, which is that was also part of evolution. Okay. Our body's tendency to store fat when you ate things that were high calorie was important in getting you from one meal to the next back in the day, right? But evolution hasn't caught up with the fact that we now have more calories than we know what to do with. And so we still have that tendency to hold on to fat. Insulin is the main hormone that makes that happen. And as a result, it's easy for us to gain weight. Okay? Now, you can cut down on that tendency to store fat in your body by increasing your muscle mass. Okay? Muscle tissue burns fat more quickly than other tissues in the body, even when you're not actively doing anything. And so if you include what we call resistance exercise in your daily activity, things like push-ups and sit-ups and stuff like that, you build muscle mass, then you're going to burn more of your body fat from moment to moment, and that's going to allow you to lose what we call bad weight, which is basically your fat weight. Saturated fatty acids have single covalent bonds between the carbon atoms, and the maximum number of hydrogen atoms, which means they're packed with calories. And those include things like butter and lard. Okay, while unsaturated fatty acids have one or more double bonds between the carbon atoms, that reduces the number of carbon-hydrogen bonds, and that reduces the number of calories. And we talked about trans fats already and how they're used, and omega-3 fatty acids, which are heart healthy. So you might wonder, well, if these unsaturated fatty acids are so good for you, then why don't we use those when we make our snack foods? And the answer is that it would reduce the shelf life. Okay, they would go rancid very quickly, and you'd have to replace them. So the easier thing to do is to just use the trans fats, but then to warn you on the package of the calorie content so that you don't eat too much. Now, phospholipids are part of the structure of cell membranes. Okay, the cell membrane is the outer barrier of the cell that allows it to permit certain things to go through when and where the cell wants. So it's sort of like a gated community. You only let in what you need, and you only throw away what you don't want. If that wasn't true, if anything could just go in or out of the cell wouldn't be able to be a living thing. Okay, it wouldn't be able to function. The other thing the phospholipid does is it allows us to build a barrier around the cell so that it has an inside and an outside, and that keeps all the cell's parts in a close physical space so that they can function. Okay. Phospholipids, which are the main building block of the cell membrane, are made from triglycerides. So what happens when you make a phospholipid is you tear off one of these fatty acids, the one that was connected to this carbon, you add a phosphate group, and then you often add another group in addition to it. And you'll notice that this part here in purple is polar or charged, right? Same thing here. This is got some polarity to it, okay? But this part is hydrophobic. It's all carbon and hydrogen. So in water, what this will do is that the greasy parts of this molecule will get with each other, and the polar parts will project out. So this thing will either form a little bubble in water where what we call the polar heads are facing the water, or it'll form what we call a bilayer, in which the nonpolar part is in the core and the polar parts are on the edges of the bilayer. And that's what makes up the cell membrane. And the reason that happens is because of the energy considerations. That's the second law of thermodynamics again, right? The easiest way to arrange water and phospholipid is to get the greasy stuff with the greasy stuff, and to get the polar stuff with the polar or the charged stuff. And that makes a stable situation. Okay? Sterols are in the tissues of animals and are not essential nutrients. We can make them from other things, but we get it from our dairy and our meat, okay? If we take in too much of it, it can build up in the arteries and promote cardiovascular disease and increase the risk of heart attack and stroke, okay? This is what steroids look like. Cholesterol is shown here, okay? Again, each bend in the ring is a CH2 group, right? So most of this is very nonpolar, right? This is all carbon and hydrogen here. This is all greasy. There's only one little electronegative atom there, that little oxygen. So this is basically a nonpolar molecule. And so it likes to associate with things like phospholipids, the fatty acid part of the phospholipid. It travels in the blood, usually inside a little phospholipid cage or embedded in the phospholipid layer, okay? And its role in the body is to control how rapidly the phospholipids move back and forth in the cell membrane. It also is important for making steroid hormones like testosterone and estrogen and aldosterone and cortisone, okay? It also is an important part of bile salts, which are part of a green liquid that's made by the liver that acts as a detergent to help mechanically break down the fat in our diet, okay? Eicosanoids are made from fatty acids, and they include prostaglandins, which are important in blood clotting, controlling blood pressure, inflammation, and labor. Other fat-soluble compounds in our diet include the fat-soluble vitamins A, D, E, and K, and lipoproteins, which are part of structures called HDLs and LDLs and HLDLs and chylomicrons. Basically, they serve as part of the vehicle that moves fat-soluble stuff around the body in the bloodstream. Okay, it's the fat-soluble stuff wouldn't normally travel in the blood. It would just form a big blob, okay? An important point about things that are fat-soluble, okay, is that it's real easy for fat-soluble compounds to cross our skin, get into our blood, and then from there go anywhere in the body they want, okay? Which means that you can overdose on fat soluble vitamins because the body has a lot of fat in it, and as a result, the stuff can build up there, okay, and it can get to toxic levels. Example of the danger of fat soluble compounds comes from a compound you may have heard of called LSD, okay? Lysergic acid diethylamide, which is what LSD is, was a hallucinogen which was popular in the 60s and is still used today by some people. And it is fat soluble. When people did LSD in the 60s, they would put it on a sugar cube, or they would take a crystalline form of it and put it on their eye. They call window pane, and it would go into their blood and from there into their brain, and then they would have a hallucinogenic experience. Well, what they didn't realize is that it was a fat soluble compound, and it ended up getting absorbed into some of the fatty tissue that's in the nervous system, okay? There's a substance, for instance, called myelin that is fat soluble that can absorb stuff like LSD. And myelin is normally used to insulate nerve cells so that they can function properly. But when they absorb a lot of this drug, what can happen is years later, the compound can leak out of the myelin, and it can affect the way that the nerves work. And so these people would have what are called flashbacks, where they would re-experience a hallucinogenic event because of the release of residual LSD, okay? The same thing also used to happen back in the early 1800s. People used to wear a lot of hats back then, and one of the parts of the hat was the hat band. And for reasons I don't still understand, they used to treat the hat bands with an element called mercury, which occurs as a non-polar element. It's one of the few metals that's a liquid at room temperature, but it can sink right through the skin and right through the blood and into the brain, and can damage nerve cells. And so you may remember from a story that you heard when you were little called Alice in Wonderland, a character called the Mad Hatter, okay? And that was based on a real effect of mercury in people that owned hat stores, because they would try on a lot of hats and they would absorb a lot of mercury, and that would affect the way their brain worked, okay? Back when I was in school, they used to sell something called tan in a bottle, okay? Tan in a bottle was large amounts of vitamin A, which if you've ever smelled it, smells like carrots. That's where you get a lot of the vitamin A in your diet from your orange and yellow vegetables. And these vitamin A pills would arrive, and you would take them, and in about 2 or 3 days, you would turn orange. And the reason that a lot of kids did that back then was because they couldn't afford to go to Florida on spring break, so they took the tan in a bottle to pretend they got a tan, right? But what they didn't realize was they were taking close to toxic levels of vitamin A, okay? And it would leach out of their skin eventually, and most of it eventually fade away, okay? So fat-soluble compounds are dangerous because of what they can do. Some examples of other dangerous fat-soluble compounds include lead, okay? There used to be lead in paint and lead in gasoline, and it would sink through the skin and into the blood and into the brain, and it would damage nerve tissue, okay? So we stopped using that. Another place where fat-soluble compounds are found is in tattoo ink, okay? So you want to be careful when you're getting tattoos. You want to make sure that they're not using stuff that's been shown to be damaging that's fat soluble, right? If the tattoo ink didn't have fat soluble compounds in it, the tattoo would fade away real quick, okay? So just a little sidebar there, okay, about fat soluble compounds. The liver's job is to take fat soluble compounds and turn them into something that is water soluble so that the kidneys can clear it out of your blood and you can pee it out, okay? But a lot of times if you take too much of a fat soluble compound, the liver can't do that work, okay? So the chemical group of fats called lipids are available in dark meat, in poultry skin, in dairy food, in added oils or fats, okay? It's an essential nutrient in the body, and it's a concentrated form of energy. It's packed with calories, okay? It's important in hormone production, structural material for cell membranes. We don't have cell walls, and protective padding for vital organs and maintaining body temperature and insulating nerve fibers and absorption of fat-soluble vitamins. So that's stuff we've already talked about, okay? Triglycerides are a total of 98% of the fat in food. They combine with glycerol to supply energy for the body, allow for fat-soluble vitamin transport, and form adipose tissue that protects your internal organs. Saturated fats are solids at room temperature and come from animal sources, and unsaturated come from plant sources and tend to be liquids at room temperature and are going to reduce your cardiovascular risk if you cook with them, okay? Sources of monounsaturates include olives and canola oil, and avocados, peanuts, and nuts. Sources of polyunsaturated, corn, wheat germ, soybean, safflower, sunflower, and fish. Essential fatty acids you have to have in your diet in order for your body to function. So you have to eat them in order to get them. They're made from the breakdown of fat. Essential fatty acids include omega-3 and omega-6, and are used to support blood clotting, blood pressure maintenance, inflammation, and other metabolic processes, okay? And those are those eicosanoids that we were talking about earlier. The AMDR for fats is 20 to 35% of your total calories. 10% or less should come from saturated. A diet high in fat is going to be linked to cardiovascular disease, hypertension because of the atherosclerosis, and diabetes type 2, okay? The exception is for children under 2 who need a high amount of fat to make brain tissue. A diet with less than 10% fat doesn't provide the essential fatty acids for the body to function, and we exhibit something called cachexia, which is a skin and bone appearance because of the lack of fat under the skin. Most of the lipid metabolism occurs after the fat gets to the small intestine. The gallbladder produces bile that emulsifies it, and the lipase from the pancreas helps to break down the triglycerides into fatty acids and glycerol. And then that gets absorbed not into the blood at first, it goes into the lymph as structures called micelles. They then become lipoproteins, and eventually they rejoin the blood at the subclavian vein, which is right under your collarbone, okay? Intestinal cells absorb the majority of the end products, with some of it being lost in the feces. VLDLs carry triglycerides to cells. LDLs also carry them to cells. And HDLs remove cholesterol from the cells and transport to the liver where we can get rid of it. So when you do your blood work, you want to be high in the HDLs and low in these two classes, because that means that you're eating heart healthy and you're less likely to get atherosclerosis, okay? Lipids are the calorie champ. They give you 9 calories per gram of energy, and they're the densest form of stored energy, right? So you don't need to eat a lot of fat to get a lot of calories, okay? All right, that brings us to the end. We're done. Does anybody have any questions before we bump out?
No, sir. Thank you.
Good? All right. I will see y'all next Thursday. Remember to email me your homework.
All right. Good night.
Good night.
Okay.